as I have said, this unit it's a little bit different to try to understand this, okay? This whole class has been a little bit different of trying to understand everything. Because trying to figure out, second order systems, quite frankly, it's hard. And then now we're getting into a place where now we're dealing with oscillating second order systems. The math here is different, but just bear with me, okay? This is the last weird thing that we have to deal with in this class. After this, it gets surprisingly simpler, even though it's another change for the way that we look at things, because we're going to be looking at data instead of power management. And as soon as we do that, then things make a lot more sense, and I don't know, we've been through a journey. So let's talk about phasors. Okay. Make sure you set your phasor to stun. The idea behind phasors is that writing a sine omega t plus phi is hard. So we don't. We write it like this. Yep. We don't even write the omega t. Typically we don't. Now you'll have some people that write the omega t plus phi. You will see some times where that is referenced. But ultimately, this is usually how it's written, and this line actually goes all the way underneath that. Okay. So what we have here is, it's just a shortened notation. And I'm going to go through and explain this a little bit before we jump into how to add these together. Okay, let's say what we're going to do is, I know I introduced sine, but let's say we're going to put everything in terms of cosines. Okay? And no matter what we face, whether it's a cosine function or a derivative of a cosine function, we really only care about the cosine aspect of it. Okay? So our goal is we're going to get everything in terms of a cosine function. Once we have it in terms of a cosine function, we're good. Okay, so let's say we have cosine of let's say we have 12 times the cosine of omega t plus 30 degrees. Okay. What we have here is 12 times the real component of e to the I omega t plus 30 degrees. I wrote real in here because it's a function that eliminates the imaginary part of everything that's in this parentheses. Okay, this is just using Euler's expansion, where from this, e to the I omega t plus phi is equal to cosine omega t plus phi plus I sine omega t plus phi. Well, that phi was backwards. Okay? It's just Euler's identity there. Hey, Igor. So the whole reason why we're doing this is if we take the real component of this, we are only focusing on the cosine piece. There's a reason why we're doing that. Saldi, I'm going to drop that monitor. I can do it. I've done it for other classes.
I can move it easier.
Actually, it's easier to move the monitor.
I bet you can.
You know what? I'm moving this monitor no matter what you want.
All right. Yeah. Take that.
Take that.
Yeah, you know what? I hate that monitor.
Accidentally break them off here. Oh.
Well, yeah. I don't know. I can't. Unfortunately. Okay, so all we're doing here is we're taking 12 times the real component of e to the I omega t plus 30 degrees. Okay? Now, how do you how can you simplify this function? Does anybody know? Two to the 2 plus 4. See you, Trace. What is this equal to? It's 2 to the 6th, right? Which happens to be equal to 2 squared times 2 to the 4th, right? So what we can do to get rid of a plus sign is separate them this way. So e to the x plus y is equal to e to the x times e to the y. It's just a simplification tool in math. We're going to do that down here. 12 times the real component of e to the I omega t plus 30 degrees, or phi, is equal to 12 times the real component of e to the I omega t times e to the I times 30 degrees. Okay, so this allows us to break it up a little bit. Now let's say we were going to take this function and add it to, so you have, what, 12 cosine omega t plus 30 degrees. Let's say we were going to add this to 4 times sine of omega t plus 20 degrees. In our standard math notation, this is very difficult to put together. Because this becomes a complex interaction of sines and cosines. The whole reason why we do this is because this adding feature right here allows us to break it up. And it allows us to do some fun math. I use the word fun, I know, sorry. I'll change batteries real quick. Okay, so if we take this boils down to this. So we'll go ahead and rewrite this as 12 times the real component of e to the I omega t times e to the I times 30 degrees. Okay, and we'll go ahead and add this to 4 times whatever this is. Okay? We're going to do a little bit of work to get this into that function here. First thing we have to do is we have to take, this is a sine function, we have to take this and convert it into a cosine function. So as you remember earlier, what sine omega t is equal to cosine omega t minus 90 degrees. I wrote it backwards, didn't I? Yep. Cosine omega t is equal to sine omega t plus 90 degrees. That's minus?
Yeah. The way that you gave it to us.
I gave it to you backwards? Dang it. Sine equals cosine z minus 90 degrees. Yeah. Well, this is also true. It's just the other way around. Yeah, because, yeah, the way that I gave it was sine is equal to cosine omega t minus 90 degrees. Okay? I never remember whether it's a plus or a minus. But what we can do here, then, is we can use this function to convert a sine into a cosine. Okay? So 4 sine omega t plus 20 degrees is equal to 4 cosine omega t plus 20 degrees minus 90 degrees. It's that easy. Slapping a minus 90. You do have to remember this formula though. I would write this in a place where you can find it. I have to look that formula up every time. So write that somewhere you can find it, because you will have to use it a couple times. Okay, so now it's just a matter of this becomes equal to 4 cosine omega t minus 70 degrees. Okay, now it's already in the formula. We can go ahead and replace this with a cosine. Oh, nope. Sorry. This is equal to 4 times the real component of e to the I omega t times e to the I times negative 70 degrees. Okay, and then we take this, we plug this up here. So 4 times the real component of e to the I omega t times e to the I times negative 70 degrees. Okay? Now, the whole reason why we did that was because we can now add these functions. You'll notice both of these functions have e to the I omega t in them. Does anybody need this, or can I erase this? Hearing no objections, he maliciously removed it from the board. So I'm just going to go ahead and say we're only looking for the real components in this entire equation. I'm going to need to go find that. We're only looking for the real, so I'm just going to go ahead and write real out front. Put everything in brackets. And what we're now dealing with is the real component of 12, e to the I omega t, e to the I times 30 degrees, plus 4, e to the I omega t, e to the I times negative 70 degrees. Put that in brackets. Okay? This shouldn't be too hard to add together now, right? Well, it's not, but you are going to have to know how to use right triangles. Because this implies that there is, well, first of all, we have the I omega t in both of these functions. So we can take that out. Becomes e to the I omega t times 12 e to the I times 30 degrees plus 4 e to the I times negative 70 degrees. And since we're only looking for the real components to this, all we're looking for is really the sine part, the cosine part of this. Because the cosine part, what you end up doing in this graph is you come up with a vector where you start at 0, and this is the real axis, and this is the imaginary axis. Okay? A point located right here has both a real value and an imaginary value to it. As I'll show you. This breaks up into real e to the I omega t of 12 cosine 30 degrees plus plus 12 times I sine 30 degrees plus 4 cosine of negative 70 degrees plus 4 times I sine negative 70 degrees. Okay? That's just writing it out. What is the cosine of 30 degrees? Hold on, I got this. Boop, 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 boop. This becomes the real component of e to the I omega t of 12 times 0.866 plus 12 times I times boop, 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 0.5 plus 4 times boop, 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 boop. Whoa. 0.342 plus 4 times I times boop, 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 boop. Negative 0.9397. Okay? Well, now we can just multiply these together. Now you'll notice this component is real. This component is imaginary. This component is real. This component is imaginary. Nice. You can add the imaginary components and you can add the real components. So, we will add this one to this one and this one to this one. The imaginaries add, the reals add. So I'm going to go ahead and draw a big R over here, big I on top of that one, R on this one, I. Your I's are going to add, your R's are going to add. The end result is going to be R plus R, I plus I, added to each other. And we're going to get a vector equation that's going to look like some real number plus some imaginary multiplied by I. Okay, this is not too dissimilar to the idea of, having the I hat plus the J hat. That's basically what we're doing. But here our I hat is 1 and our J hat is I. That makes any sense? All we're doing is getting rid, well, we're just combining real and imaginary numbers here. I'm sorry, baby, I didn't mean to throw you. Okay, so some quick maths. $12 times 0.866 is equal to, so this becomes the real value of e to the I omega t times 10.392, which is the first one, plus 6i, which is the second one, 4 times 0.342 is 1.368, which is the third one, plus 4 times negative 0.9397 is equal to a negative 3.7588i. So again, this one's real, this one's imaginary, this one's real, this one's imaginary. We'll combine our reals, we'll combine our imaginaries. So this becomes, we want the real aspect of e to the I omega t times 11.770? Nice. 6. Dang it. That's a 6. Plus, growth. It's going to be a 2.2412i. It's just this plus this. And now we have a brand new function. Well, guess what? We can take that and break it into, well, a couple of different values. We could take this and plug it back in and try to figure out this is equal to, what's sine, this is equal to some number a times cosine of theta plus that same number a times I sine of theta. These are equal. To figure out the value of a, the maximum value occurs when this is all real. So the maximum value occurs when you take the square root of 11.76 squared plus 2.2412 squared. Now all that we're doing here is, again, we're going back to our axis. Here we've got 11.76 on the real, 11.76, and then we have 2.2412 on the imaginary. And what we've done is we've drawn a vector that is that long. This is the vector representing the sum. It has a real component, it has an imaginary component. Okay? This right here is a right triangle, where your x component is your real and your y component is your imaginary. So when you're calculating the length of that line, the total length of that line is equal to the length of the hypotenuse of the triangle, which is why I use this formula. That is the correct expression by which you should look at what we're doing right now, by the way. Because when we started this class, we didn't know we were going to be using imaginary and real numbers. And now we do. And the whole reason why we do it is just so that we can add sine and cosine functions together. Okay? So the idea is if we were to draw this line, a value with the exact same r value and just a different theta would trace a circle. Okay? We're looking at one very specific theta angle. But if we wanted to know what r was, I mean, r would be different than the angle theta. Theta represents this line that extends out to infinity. R represents this circle that captures this point, where this is the radius of that circle. So here this is A. Guess not R, it's A. So let's calculate out what A is equal to, just using our hypotenuse formula. So I get A is equal to 11.972. Okay, how do you find theta here? So just converting polar and Cartesian coordinates at this point. The Cartesian coordinate axes are given in real and imaginary units. It's your I and j. And your polar coordinates are the length of that line and then the angle that the line is at. How do we find theta? Anybody remember your trig identities? Yeah. It would be inverse tangent. Now, we did calculate out the hypotenuse, so you could use sine cosine, but here just to eliminate that error, inverse tangent is the best way to do it. Okay? So here we know tangent of theta is equal to your imaginary component divided by your real component, which here is equal to 2.2412 divided by 11.760. Okay, so theta is equal to the inverse tangent of this, which that's equal to 0.1906. So theta is equal to 10.79 degrees. So, at the end of this problem, our end solution is the real component of all of this becomes real e to the I omega t times, now we know what this is. This is 11.972 times e to the I times 10.79 degrees. And if we take the real component of this, we then just throw it back in. These are multiplied by each other, which means we can go ahead and add the I omega t back into here. And what you end up pulling out of it is this is equal to cosine, 11.972. Write this so it's readable. Cosine of omega t plus 10.79 degrees. That was gross. Let's not do that. That is the right answer. But that was a lot more math than, remember, we don't like doing math. So let me introduce the simpler way of doing it, which, yes, we're still going to have to do this, but we're going to skip pretty much everything leading up to this. And we're just going to focus on this thing and this thing. Caden, you good? Okay. Your quiz for next week is going to be lit. All right, so the problem I'm giving you is we have two functions. We're going to go ahead and say it's 5 cosine omega t plus 10 degrees plus 3 cosine omega t minus 80 degrees. And you know what? For funsies, let's add the third one here. Plus 2 cosine omega t. Because why not? So we can go back through all of the steps that we did for the last problem, which I expanded to try to explain why we were doing what we were doing, or we can just solve it. Let's do it that way. This is equal to 5 times cosine of 10 degrees if we pull out the omega t for right now. And just focus on looking only at your phase angle change because omega t is constant between all of them. We can go ahead and write this as 5. Well, we can go ahead and just pull out the e to the I omega t, multiply that by 5 e to the 10 degrees, I times 10 degrees, plus 3 e to the I times negative 80 degrees, plus 2 e to the I times, what, 0 degrees? Is that right? Does this have a phase angle of 0 degrees? Somebody back me up. Because, I mean, I could have written a plus 0 in here, right? And this would have had, I mean, it would have resulted in the same thing. Feel free to correct me. I know I'm right. I'm just making sure that you know I'm right. That's how I play my game, so. All right. So now we're going to have to break these into real and imaginary components. So this step here, we converted into Euler's equation. We're going to then take Euler's equation and break that up. So 5e to the I times 10 degrees has a real and imaginary component. The real component is 5 cosine 10 degrees. That's the real component. Plus 5 sine, so it's I times, 5 times I sine 10 degrees. And that's the imaginary component. Plus 3 cosine negative 80 degrees. That's the real component. Plus 3 times I sine negative 80 degrees. And that's the imaginary component. And then you have 2 cosine 0 degrees. That's the real component. Plus 2 times I sine 0. That's supposed to be 0. And that's the imaginary component. Does anybody have questions as to how I got here? Because I can go through my reasoning. This is step 3. Anybody need me to go back and explain this again? Any brave soul willing to admit they're lost? Or am I just that great of a teacher? I mean, I'm willing to, thank you. I'm willing to take that, but this is confusing. Dylan, do you want me to explain it again?
I'm confused about, so the cosine and sine. In the original function, you have cosine.
Yes.
If you had sine, would it be switched down there?
If we had sine, what we would have had to have done is we would have had to have converted it into a cosine. Okay. So if this was sine omega t plus 10 degrees, we convert it into cosine by saying this is cosine omega t plus 10 degrees minus 90. And then we would go right back into this. Okay? So ironically, we take this from a cosine function to an exponential function back to a cosine function. And the whole reason why we do this is to break this 10 degrees out. That is the whole reason why we do it. Once we've broken the 10 degrees out, now all we're doing is the I omega t is over here. This is still the same function. All of these are equal. The same function, but we have broken out the phase angle on each one of these so that we can add them together. You are never going to have a system that has a different omega t, that has 2 different omega t's. Or God spare your soul. Hopefully you never do. Okay? Omega t is a function of the system itself. It is part of the forcing function. If you remember back to that, the forcing function here means that your behavior is always going to fall into an omega t result. It's always going to be some function of a sinusoid that has an omega t. It's the whole reason why we're doing this. Transient function also happens to have a sinusoidal feature. It's just everything gets combined into a cosine-sine relationship. Okay? So, we take our cosine function, turn it into an exponential function, turn the exponential function back into cosine functions. This breaks out the phase angle and allows us to combine these now. Okay? So now we just take our real components and our imaginary components, and we add them together. I'm going to go ahead and start by calculating all these numbers. So 5 times cosine of 10 degrees. This is equal to, so e to the I omega t times 4.924 plus 5 times sine of 10 degrees, 0.868i plus 3 times cosine of negative 80 degrees See if I can do things on my calculator. It's equal to 0.521 plus 3 times I sine of negative 80 degrees is equal to, this becomes a minus 2.954 I plus 2 times the cosine of 0. I know the answer to that one is 2. And 2 times I sine of 0 becomes 0. Okay, so here we have a real component, we have a real component, we have a real component, we have an imaginary component, we have an imaginary component, we have an imaginary component. We sum our reals, we sum our imaginaries, and we go off of that. So, I do this in my head, but I'm tired. 4.924 plus 0.521 plus 2. Well, that is not right. So this becomes E I omega t of 7.445 plus 0.868 plus, oh, that's a minus, 2.954 plus 0 is equal to minus 2.086i. Okay? We then calculate the magnitude of this vector. So we have A is equal to square root 7.445 squared plus 2.086 squared. Yes, I know there's a negative in there, but it squares out. This becomes 7.732, and our angle theta is equal to the inverse tangent of our y over x, which is equal to the inverse tangent of 2.086. That's a negative. Got to keep the negative in here this time. 7.445, and that is equal to no, not an error. Negative 15.65 degrees. So our final answer is, well, if we just keep writing this out, E omega t 7.732 e to the I times negative 15.65 degrees, which just means that we have 7.732 cosine omega t minus 15.65 degrees. And that's our final answer. Okay. Is this making any more sense? If I handed you the problem, could you do it? Huh? Well, guess what? I'm about to hand you a problem. Let's do one more. One more, and then I'm going to hand you a problem, okay? You all got to figure it out as a class. Bum, bum, bum. This time, we're just going to use phase angles. So, I have 2 with a phase angle of -10 degrees plus 5 with a phase angle of -90 degrees. Okay, and you can find this by figuring out sines and cosines. All this means is you have 2 cosine omega t minus 10 degrees plus 5 cosine omega t minus 90 degrees. Now, the interesting thing about this is those are equal. That is 5 sine omega t. Okay, now 5 sine omega t is equal to 5 phase angle -90 degrees. Just for funsies. So, jazz hands. All right, so we have 2 angle 10 degrees, 5 angle -90 degrees. The real component of this becomes 2 cosine -10 degrees, it's the real, plus 2 times I sine -10 degrees, that's the imaginary, plus 5 cosine -90 degrees, that's the real, plus 5 I sine -90 degrees, that becomes the imaginary. So 2 cosine -10 degrees, actually calculate that out. This is equal to 1.970 plus 2 sine -10 degrees. This becomes a minus 0.347 I plus 5 times the cosine of -90 is 0, isn't it? And then this becomes minus 5 I. And then we just add them up. You add the reals, dink, dink. You add the imaginaries, and we go from there. So this becomes 1.970 minus 5.347I. Your final answer is going to be the hypotenuse of this times the phase angle. So it becomes 1.9700 squared plus 5.347 squared times the phase angle of the inverse tangent of -5.347 divided by 1.970. Look, I even put it in the final form. And I would just calculate them out. So this is equal to 5.698 times the phase angle of -69.77 degrees. And that's the final answer. Okay, in lieu of giving you a break, I'm going to hand you a problem, and this is going to be the last thing we do today. I want you to solve the problem. I want you to tell me the answer. If you want to take a break before solving the problem, that's fine. Bothers me none. But here's your problem. 2.3, phase angle, 15 degrees, plus 1.4, phase angle, negative 40 degrees, plus 1.8, phase angle of 70 degrees. What is the final answer? Give it to me in phasor form. And that's all we're doing for the rest of class, so yeah. Are you done already? No. Kidding.